Hey, you ever stop and think about time? Like, really think about it.
Mm.
You ever had that weird feeling where, an hour just vanishes, but then 5 minutes can feel like forever?
Oh, definitely.
Well, get this. It might not just be in your head. According to Einstein, and this pretty credible book we're looking at today, time can actually tick differently for different people.
Sounds like science fiction, doesn't it?
Totally.
Yes.
But it's a real head scratcher,
Yeah.
apparently baked right into how the universe works.
That's right. We're taking a deep dive today into, well, time dilation.
And our guide for this mind-bending trip is Stephen Weinberg's Gravitation and Cosmology Principles and Applications of the General Theory of Relativity.
Yep, that's the one. It's a heavyweight text.
It is, yeah. Definitely not beach reading, let's be honest. It's a serious piece of work.
For sure.
But don't worry, we've done the intellectual heavy lifting, kind of dug through it to pull out the really fascinating bits about how time works. Or maybe it doesn't work the way we think.
Right.
So our mission today, let's try and unpack this wild idea of time dilation straight from, a foundational physics text.
Yeah.
And just see how strange things can get.
Sounds good. So let's start with the basics. What actually is time dilation?
Okay, yeah. Lay it on us. What are we talking about here?
Well, simply put, time dilation just means time doesn't tick at the same rate for everyone. It's not universal.
All right.
It can speed up or slow down depending on two main things: how fast you're moving compared to someone else, and how strong the gravity is where you are.
Speeding gravity.
Speed and gravity. And look, this isn't just theory. It's been measured many, many times.
Wow. So speed and gravity can literally warp time.
Mm-hmm.
Where does Weinberg's book start with this?
Well, Weinberg builds it up carefully. Part 2 of the book covers special relativity.
Yeah.
That really gives us the first piece of the puzzle, how motion affects time.
Special relativity, right? That's Einstein's 1905 thing.
Yeah.
What are the key ideas there that lead to time bending?
There are two big ones. First, the principle of relativity itself. The laws of physics, they're the same for everybody moving at a steady speed, no special viewpoint.
Okay, makes sense. Laws are laws.
And second, and this is the one that really twists your brain, the speed of light in a vacuum is constant, always, for everyone.
Right, no matter how fast you're moving or where the light's coming from.
Doesn't matter, it's always the same number.
That still feels so weird. How does this mess with time?
Okay, try to picture this. You're standing still, got it.
Yeah.
And someone flies past you in a super fast spaceship. Really fast.
Okay, zoom.
Now imagine a light beam shines from, say, the floor to the ceiling inside that ship. For the person inside, the light just goes straight up. Simple.
Right.
But for you, watching from the outside, the ship is moving sideways while the light is traveling up. So from your point of view, that light beam actually travels a longer diagonal path, doesn't it?
Yeah, because the ship moved while the light was in transit.
Oh, okay. Exactly. But crucially, the speed of that light has to be the same for both of you. That's the rule.
Okay, still with you.
So if the light travels a longer distance for you, but its speed is fixed, the only way that works is if time itself is passing slower for the person on the spaceship relative to you.
Wait, what?
Their clock has to tick slower than yours to make the math work, to keep the speed of light constant for everyone. Their time stretches.
So if my buddy is blasting through space near light speed, their watch is literally ticking slower than mine back here.
That's nuts. Is there like a formula for that? How much slower?
Oh, absolutely. There's a precise mathematical relationship. It involves something called the Lorentz factor. Basically, the time interval for the moving observer gets multiplied by this factor from the stationary observer's perspective.
Yeah, this factor gets bigger the faster they go.
Exactly. The closer you get to the speed of light, the bigger the factor, and the more their time slows down relative to yours. Approaching light speed, time would almost stop for them, from your point of view. Mind blown. Okay, that's the speed part. But you said gravity, too. How does Like gravity, the heavy hitter, get involved in warping time.
Right. Okay, so that moves us from special relativity to general relativity, which Weinberg covers in part 3. This was Einstein's next big leap. He realized gravity isn't quite a force like we usually think of it.
Not a force.
And what is it?
It's the curvature of space-time. Imagine space-time as a fabric. Mass and energy, like planets and stars, they warp this fabric, create curves and dips in it.
Okay, the classic bowling ball on a trampoline analogy.
Sort of, yeah. And just like objects follow the curves on the trampoline, things moving through space-time follow the curves created by mass and energy. That's what we perceive as gravity.
Space-time curvature.
Okay.
Still a bit abstract, but how does a curve in space affect the flow of time?
Well, time is part of that space-time fabric. So if the fabric is warped, time is warped too. Think of it like this. The stronger the gravity, the deeper the curve in space-time, the slower time flows.
Slower and stronger gravity. Yep. And conversely, time passes faster in weaker gravitational fields, further away from the source of the gravity.
Okay, give me an example. Something, maybe a bit more down to earth.
Sure. Imagine someone living way down in a deep valley versus someone living up on a high mountain.
Okay.
The person in the valley is slightly closer to the center of the Earth, so they're in a slightly stronger gravitational field.
Right, makes sense.
So, incredibly, slightly, almost unnoticeably in human terms, time would actually pass a tiny fraction slower for the person in the valley compared to the person on the mountain.
No way, really.
Yes, the difference is minuscule for mountains and valleys, but it's real, and it's measurable with atomic clocks. Weinberg mentions the Pound-Rebka experiment.
Ah, right. You mentioned that.
Yeah, it didn't go into huge detail in the bits we focused on, but it essentially measured the effect of gravity on the frequency of light, which is related to time, confirming this gravitational time dilation right here on Earth.
So hang on. If I spend my whole life living in a basement apartment and my identical twin lives in, like, the penthouse suite of the tallest skyscraper, they'd actually age a tiny, tiny bit faster than me.
Technically, yes. Over a lifetime, the difference would be incredibly small, nanoseconds maybe, but according to general relativity, it's there.
That is just wild.
It is, and while it's tiny here, think about extreme gravity, like near a black hole. The time dilation becomes enormous.
Right. And, it suddenly clicks. This isn't just weird physics trivia, is it?
Yeah.
You hear about GPS needing relativity.
Exactly. That's a perfect real-world application. GPS satellites are moving fast, and they're in a weaker gravitational field than we are down here.
Ah, so both effects are at play.
Both effects. Special relativity says their clocks should tick slower because they're moving fast. General relativity says their clocks should tick faster because they're in weaker gravity.
Okay. Which one wins?
For GPS, the gravitational effect, faster clocks, is actually larger than the velocity effect, slower clocks. But you have to account for both precisely. If engineers didn't factor in relativistic time dilation, your GPS would send you miles off course within, like, a day.
That's amazing. So this warping of time, even though we don't notice it walking around, is actually built into technology we use every single day.
Absolutely. It shows how our everyday intuition about time being this absolute constant thing, it's just an approximation that works well at human scales. But fundamentally, it's wrong.
Yeah, our perception is just limited.
And that's what's so powerful about delving into a source like Weinberg. It takes you from these fundamental principles, like the constant speed of light and space-time curvature, to this completely different understanding of time. It's not a universal metronome.
No, it's bendy.
It's flexible, yeah. It's interwoven with space, with motion, with gravity, part of the cosmic fabric.
It reminds me of this time I was stuck waiting for a seriously delayed flight. Every single minute felt like an actual hour, right?
Oh, yeah, know that feeling.
But then, other times, you're having fun with friends, and boom, 3 hours just vanish. It's like my own personal subjective time dilation.
Yeah. Yeah.
But the fact that the universe itself does this objectively based on speed and gravity,
Yeah.
I mean, that really forces you to rethink things, doesn't it? It's
Uh,
not just how we feel time pass, it's how it actually behaves.
Exactly. And that's the key insight here. It's less about memorizing the Lorentz factor, maybe, and more about grasping this profound shift. Time is relative.
Right. Not absolute.
It's part of space-time, this four-dimensional thing that gets shaped and stretched by how things move and where they are in a gravitational field.
Okay, so boiling it down,
Mm.
thanks to Weinberg and Einstein,
Mm.
time isn't rigid.
Mm-hmm.
It stretches with speed, it slows down with gravity.
Mm.
It depends on the observer. It's
Mhm.
relative.
That's a pretty good summary, yeah.
So, okay, final thought here. The big question that's kind of buzzing in my head now. If time can be this fluid, this changeable thing, what does that actually tell us about, the fundamental structure of reality? Could our whole experience, which feels like it's built on this steady flow of time, be way more, I don't know, interconnected and flexible than we usually assume?
That's a deep question.
It's just weird to think my now might not be the exact same now as someone else's just because they're moving differently or somewhere else gravitationally. It makes you wonder what other things we think are solid might be a bit squishier.
It absolutely does. And that's why exploring these ideas is so important, I think. Understanding the relativity of time, it really opens up entirely new perspectives on the cosmos and, well, our own place in it.
Definitely food for thought.
All right.
Well, this has been another fascinating deep dive. My brain feels a little stretched itself today in a good way.
Happy to help bend it slightly.
Huh. Until next time, keep questioning.